Okay, so in this video, we are going to start with analysis of the beam, where a train of concentrated loads are moving over. So fourth, last condition is when there is a train of concentrated loads or a train of point loads. Okay. So we have seen a single point load moving, UDL longer than the span moving, UDL shorter than the span moving. For all these, we have seen what are the conditions and values for maximum negative and positive shear force at a section C, maximum bending moment at a section C, and we have seen what are the absolute maximum, isn't it? Now, what happens when there is a train of concentrated loads? For this, we will be finding out not three, we will be finding out four things. First one is maximum shear force at C. Okay. Then maximum bending moment at C, right? And then you have to find out what is the absolute maximum shear force anywhere on the beam. Okay. Anywhere on the beam. And also the position for absolute maximum bending moment on the beam. Okay, these four, just like how you did for all the cases before. So let's start with the first one, which is maximum shear force at any section C. So let us consider the beam. Okay, we are considering a beam AB, and as usual, you are taking a section C somewhere here. And let us assume that the distance AC is Z and the span of the beam is L. So this is A and this is B. Now when we say there is a train of concentrated loads, let us assume that we have a set of four loads, W1, W2, W3 and finally W4. Okay. So these are moving from left to right. We are assuming it's from left to right. It can also move from right to left. Okay. Now let us just let us just draw the ILD for um, it's going to be slightly different because a set of loads are coming and we also don't know what are the magnitudes of W1, W2, W3, W4. Maybe W2 is bigger than W1. There are a lot of combinations which is available, which is possible with these set of loads. So we have to think before we draw the ILD for shear force at C. We cannot draw the same shear force diagram you have been drawing for all the cases before. So let us just analyze. We are starting with W1. Okay. So as soon as W1 enters a span in the sense it has started with A and then crossed A. So as usual, there is a negative shear force happening, which goes on increasing as the loads move on. Okay, that is what we have been learning since the past derivations and past explanations. So that develops a maximum negative shear force with the maximum ordinate of Z by L. All that is fine. Now, some more loads may enter the span. That is, first W1 has only entered. So that is actually the case of a single concentrated load. But depending on the spacing between these loads, again the next W2 will be entering. Okay, and then W3 will be entering, W4 will be entering, etc. So the rate of increase of that shear force will go up, isn't it? It will go on. So this continues till your W1 has reached the point C. So now the W1 has reached the point C. So now W1 is at C and the rest of the three other loads are on span AC. So that is the condition where there is a negative shear force, maximum negative shear force, isn't it? Now, as soon as the W1 crosses C, okay, now W1 has moved beyond C, then what happens is, you know that it moves to a positive shear force. So, there is a reduction in the negative shear force or there is a drop in the shear force value. So, further movement of loads will again cause an increase in the shear force till the second load reaches C. Then there is a second peak value or a second drop when the second load crosses. Like that, every time the load crosses the section C, there is a peak value or the shear force value goes on increasing. Now you have to calculate the highest value among these trials. That is, you cannot say that when W2 has crossed, you get a maximum. Maybe sometimes when W3 has also crossed, you get furthermore maximum. So it is important to consider at least two trials, and then the highest of that value is treated as the highest positive shear force. So that we will see when we do a problem. I'll show you how it's being checked. So it means that as the loads cross the section C, there is actually an increase in the shear force and there is no drop. So that is why the shear force diagram looks like this. There is a slight increase in the shear force value and it's not dropping to 0 at B. Okay. The ordinates remain the same, L minus Z by L and Z by L. Okay. So this is about positive and negative shear force. So the what you can write here is uh, there is a when W1 reaches reaches the point C or section C, you have a maximum negative shear force at C. Okay, and once W1 crosses C, there is a drop in the negative shear force and increase in the, that means there is a positive shear force developing. Then as W2 crosses C, what happens? There is further increase in shear force. As W3 crosses C, again there is a more increase in shear force. So it means that as all loads cross C, the shear force goes on increasing. That is what we understand. Hence the diagram which we have sketched here. Okay. I hope that's clear. So how to select the highest value? You have to check, position the load such that two are to the right and two are to the left, and then check what is a positive shear force or negative shear force which you are getting, and you have to report which one is the maximum that you can take as a maximum value. Okay. So for as a note, if you want to sum up, you can write for maximum negative shear force. For maximum negative shear force, what is the condition? Most of the loads, okay, because we don't know which one gives you the maximum. Maybe one load to the right and rest of it to the left might give you a maximum negative shear force. You have to check that. Most of the loads will be on the left of the section selected. Okay. And for maximum positive shear force, most of the loads will be on the right of the section. Okay, after checking some trials. So this is what you can infer for maximum shear force at C.